People are still filing in, but I think we can get started. So good morning, everyone. Thanks for making it out to the multi-cluster track, first thing on the first day of KubeCon. My name's Alex, and hopefully you're all expecting me to be talking about running a system across multiple Kubernetes clusters, because that's what I'm here to do. And for anyone who's been using Kubernetes for a number of years, since the early days, you've probably noticed how much easier it's gotten to run your applications on Kubernetes. You couldn't have run a stateful system or a complicated distributed system in Kubernetes very reliably just as little as like 3 years ago. All these great features have been added for managing disks, for managing stateful applications, for running a cluster that spans multiple zones, or for running your Kubernetes cluster for you. There have also been improvements in packaging your applications so that other people can install them on their clusters with things like Helm charts and operators. But not much progress has been made in that same time in making it easy to run applications that span across multiple Kubernetes clusters. So it's very easy to look at the docs and figure out how to run something in one cluster. It's very hard to look at the Kubernetes docs and figure out how to run an application that has some nodes in one cluster over here and some nodes in one cluster over there. It's a much tougher problem that is not really written down anywhere. It's not clear where to get started. The same is true if you're trying to run across multiple clouds. It's very tough to figure out how to run an application that spans from one cloud to another or from one cloud to your on-prem environment. And so there have been some efforts over time. There was the Kubernetes project a couple years ago that didn't really seem to go anywhere. And there was the Federation v2 project that's still ongoing that we have high hopes for that should make some of this easier. But maybe people would argue that this hasn't improved just because it's not an important problem, because no one wants to run their applications across regions. But I'd propose that there are at least a few reasons why you'd want to do this. One obvious reason is latency. So more services than ever span across multiple regions and serve users all around the world. And if you want to serve users all around the world, if you're running just one single region, users on the other side of the world are necessarily going to have a really long delay whenever they want to use your service. So the solution to that is to put some instances of your service closer to them. So run some of your service in the US, some in Europe, some in Asia, or if you're just running with users in one country, span the country, both coasts. You might also run across multiple clusters in multiple regions for fault tolerance. So if a single region goes down, you don't want your entire application to go down. You might also do this for bureaucratic reasons. So if you were signed up and got your badge this morning, you probably noticed the GDPR signs. There are laws springing up in countries around the world that require you to store their users' data in certain places, often in their own countries. It's tough to do this if you're storing all of your data in one place that isn't that country. And so I do want to talk today about this experience of running an application that spans multiple clusters, why it's hard, what sort of things you need to know about Kubernetes in order to get started, and then what kinds of solutions there are out there for this problem. And before we move on here, who here has tried running an application across multiple clusters before? And who here is doing it in production? Okay, so not very many people in either group. I hope that will be a much higher number over the next year or two. I think things are going to continue improving. And I should say that I'm not here to prescribe a particular solution. I just want to talk about things that I've tried, things that I've seen users try, things that I've seen run in production, and what my experiences have been with them. I don't have a single golden solution for anyone to walk away with from here today. And just so that you know where I'm coming from, my experience with Kubernetes is that I worked on the Kubernetes and GKE team back in 2014 for a little over 2 years. I worked all across the GKE stack and contributed to open source, things like logging, monitoring, networking, cloud provider integrations. Since then, I've been at Cockroach Labs working on the open source SQL Cockroach DB database. And in addition to working on the database itself, I've led all of their container-related efforts. So making sure that users can take a configuration off the shelf and easily run it in their orchestration system of choice. I've helped them run it in different clouds, from a single zone to multiple regions, and have also had to help people with their own configurations because they didn't want to use one of ours. They made their own, ran into some trouble. So I get to see different ways of running things, even beyond the ones that I would necessarily recommend. And we have a number of users using Cockroach DB in Kubernetes, both in a single cluster and spanning multiple clusters today. So this is something that people are doing in production, including us. But the initial question you need to ask is why this is hard at all. I've talked to many people who have run a system in a single Kubernetes cluster and assume that it's going to be very easy to span to multiple Kubernetes clusters because it was easy to do so in the one cluster. And Kubernetes is supposed to make it easy to orchestrate services, right? But to make things clear, I'm using multi-region and multi-cluster pretty much as synonyms because you're never recommended to run a single Kubernetes cluster that spans across multiple regions. In the early days, you weren't even supposed to do it across multiple zones within the same region. Nowadays, you can do that with what's called a multi-zone cluster. But if you want to span across multiple regions, you're really going to want to use multiple clusters. Run a single cluster across regions at your own risk. Kubernetes hasn't been designed to deal with the latency differences between nodes and other complications. But to get started with trying to set up this multi-region application and learn how to configure it in Kubernetes, you need to understand what do these systems need. And as our example today, we're going to be looking at Cockroach DB, just because it's the one that I'm most familiar with. It's what I've worked the most with. And as a very quick one-slide refresher, it's an open source distributed SQL database. It speaks the Postgres wire protocol. Your application can talk to any of the one or more processes in your Cockroach cluster and get their SQL responses back. Internally, it's doing all sorts of work to divide your data up into ranges, replicate it across the various nodes, rebalance as nodes are added to or removed from the cluster. And it internally uses consensus and a transaction protocol to ensure you get fully ACID transactions. It also offers some geographic features such that you can tell it which locations you want it to put data in or which locations you don't want it to put data in. But the way that you run it is that you just take the single binary, start it on a number of machines, point them at each other such that they can find each other, and then it just acts as a single homogeneous cluster of nodes. There are no special roles to worry about, so we don't need to worry about that in our configurations. You just run a bunch of Cockroach nodes and make sure they can all talk to each other. And so when running in Kubernetes, Cockroach requires roughly 3 things. And these are basically the same 3 things that any application that manages state needs. So it has to have some sort of persistent storage that will be there across restarts of the pod or of the node. It has to have the ability to communicate directly with every other Cockroach node in the cluster. And it needs some sort of network address that can survive restarts. The last one isn't always needed for Cockroach, but it's needed for most stateful systems, so we can leave it in here. And you probably notice, if you've used stateful sets before, this is what stateful sets are for. So if you're in a single cluster, you get all these things built into Kubernetes, and it works really well. It's been hardened over the last couple of years. But if you're running across multiple Kubernetes clusters, that's when you start to lose these things that most stateful systems need. You lose the ability to have a network address that survives restarts, that's usable from everywhere. And in many clusters, you'll lose that ability to talk directly from every node to every other node, regardless of where they're running. And it all comes down to networking then, because these are both networking problems. We need pod-to-pod communication, even across clusters, and when applicable, across things like VPCs or other private networks. And we also need that address that can be used both within and between clusters. You could optimize this and say you're going to have a separate address for communication within and a separate address for communication between. But to keep things simple, we'll just assume we want one address that works in both cases. So Kubernetes networking is the problem. But why is it the problem? Since the beginning, Kubernetes has required a few things in order for an installation of Kubernetes to be compliant. It has to ensure that every pod has its own unique IP address that no other pod has. That IP address has to look the same to the pod itself as it does to all pods that that pod is talking to. And this has to work without any form of network address translation. This might seem very straightforward, but at the time Kubernetes was released, it was pretty revolutionary, very much against the current ways of thinking. It was different from how Docker recommended doing networking. It was different from how Google did networking internally with Borg. And so there weren't really many ways of implementing this, actually. It was hard to set up a cluster in the early days because there was no way of providing this for the pods that you were running. We wanted to run a lot of pods on each machine, but each machine in a traditional network is only given 1 or 2 IP addresses. And so since then, a ton of solutions have been built up to satisfy these requirements. If you look at the Kubernetes networking documentation page, you'll see more than 20 different solutions listed, and it's not a complete list. There are a lot of ways that this gets done out there in the wild. And because the only requirements that were specified were how a single cluster should work, the multi-cluster case is basically undefined behavior, and it's up to implementation details of each different networking solution. And so this is kind of like if you're writing a C program that has undefined behavior in it, and it works on one compiler and one CPU architecture, but then you try to compile it for another architecture, and you find that your program explodes. That's kind of the situation of trying to run a multi-cluster application across different clusters. And there are all sorts of these networking solutions out there. This is just a small sample of some popular ones. You'll notice all the cloud providers do things their own way in a way that integrates nicely into their virtual cloud networks. There are a bunch of software solutions out there that do things in different ways as well. And people have to figure out how to do this on-prem in a number of different ways, often using some of the software solutions off the shelf, but maybe doing things in hardware or in a custom way. And again, these all work differently, so there's not much you can depend upon working exactly the same if you have previously used one networking solution and are trying to set up your application on a different one. And you can kind of group them into categories, though, so you can at least do that. Some of them support pod-to-pod communication across clusters. So if you're running on GKE or Amazon ZKS, as of earlier this year for EKS, you can talk directly from one pod in one cluster to a pod in another cluster, as long as they're in the same VPC or you've done some sort of peering. So this is great. You don't have to think about it much when you're in these environments. Others don't have it on by default, but make it kind of easy to enable. So Azure's default basic networking mode doesn't support it, but if you enable their advanced networking mode, which is just like a checkbox when you create your cluster, then you get it. Cilium, which is one of those open source software solutions for providing Kubernetes networking, has a mode called a cluster mesh, where you can configure it to enable this, but it won't do it by default. But for many other software solutions, it's pretty difficult to get this pod-to-pod connectivity. So this is especially a problem if you're running on-prem clusters or if you aren't in Google or Amazon. And we don't have enough time today to fully cover how all this works. In fact, we don't have much time at all. So if you want to learn more about this, check out some past KubeCon talks. In particular, I'd call out the Life of a Packet talk by Michael Rubin a couple years ago in KubeCon Europe, if you want to get a refresher on how some of these different solutions actually route packets through a network. And so, what can we do? We know the problem is that networking doesn't provide for direct communication between clusters sometimes, and it never actually gives us an address that we can reliably use between clusters. And I tried a whole bunch of things out earlier this year in the first half of the year. I tried a dozen, maybe 10 different solutions. Tried to get them working, checked out how reliable they were when things failed. I did some thought experiments on different ways they could fail that I didn't actually try out. And unfortunately, there wasn't like a single great solution. They all have a bunch of problems, and some of them might have improved over the course of the year, but for the most part, things are about the same. So they either didn't work in certain environments at all, or they're easy to break if the operator makes a mistake, or they're a little slower in the data path, and so you're not going to get the performance you expect out of your system, or they're tough to use with TLS certificates, or in some case, you're using a third-party piece of software that isn't quite ready yet to be used in production for this usage. And I will call out that my perspective on this is likely to be a little different from some of yours, because my goal is to come up with configurations that work for as many people as possible with as little expertise needed on their end as possible. If you are a Kubernetes expert and you have like a single stable environment that you want to get things working in, your requirements will be slightly different from mine, because I'm trying to let everyone run Cockroach across multiple clusters, whereas you might just want to run something across your own clusters in your own certain environment. And I'm also not here to prescribe a particular answer, again, so take out of this what you can. So I'm going to walk through a few different solutions that were the best out of the ones that I tried. And for all of them, assume that I'm running just a stateful set in each of the separate Kubernetes clusters. And the problem is to connect the pods from those different clusters together. But in each cluster, your pods and your disks and your IP addresses will all be managed by the stateful set itself, except for in this first solution here. So in this first solution, you're basically like getting around all the Kubernetes magic. You're just ignoring it. You're saying, I don't want your scheduling. I don't want your networking. Just run me on these machines and let me use the host machine's network. So this is very similar to just running processes directly on VMs without even using Kubernetes, because you're picking which processes are running on which machines, and you're letting them use the machine's network. So this works if you don't have pod-to-pod connectivity across clusters, because even in those cases, you'll usually be able to talk from one machine in one cluster to all the machines in the other cluster. Or you can at least set that up pretty easily. So what you do is you either assign pods directly to nodes by creating a replication controller of size 1 and putting a node constraint on it, or you use a daemon set, and that way you get Cockroach running on all the nodes. And then you use the host network setting, which is like passing -- net equals host to all the Docker containers. And it lets them use the host's IP address. So this also makes some people happy who are otherwise skeptical of running stateful workloads in Kubernetes, because it removes some of the magic that makes running stateful workloads a little scarier, because you're not getting things being rescheduled underneath you. You can choose to use the machine's local disks if you want, rather than using network-attached storage, because you know the pods are always going to be running on the same machine. And so this might sound kind of silly, like you're getting rid of all the Kubernetes magic, but it's a very reliable, dependable way of doing it. And so it works even when pod-to-pod communication doesn't. It has 0 moving parts. Even some of the parts that are built into Kubernetes are no longer being used. And the only issue is that you need to make sure the machines in your cluster aren't changing a lot. Their IP addresses aren't changing. They aren't being cycled in and out of the cluster. And this could be a problem in certain cloud environments. So managed service offerings like GKE and EKS do node upgrades by just removing the VMs and replacing them with new ones. And that means the IP addresses go away. If you're using local disks, those go away. And so this is something you might not want to do in the cloud unless you've taken special precautions. But if you're running on-prem, this is great, because you don't have to worry about connecting the networks of the multiple clusters. And you can be confident those machines are going to stay there, because they're physical machines in your own data centers. This does require a bit of manual setup to get working, and it can use up ports on the host machines, so you can't run multiple Cockroach instances on the same machine, because it's using the host's ports. But this is a surprisingly good, very easy to configure way of doing things if you're on-prem. If you are running in the cloud, though, you might use the external load balancer feature. And you might laugh at this, but we have a couple of customers doing this in production, and it's been working reasonably well for them. This is the most universally feasible way, because it does not require pod-to-pod connectivity between the clusters. You're relying on the external load balancers to provide you networking from one cluster to the next. So what you do is you just create a separate load balancer for every Cockroach pod that you want to run. So if you're running 3 pods in each of 3 clusters, you're going to end up with 9 load balancers. And then you just have all the pods talk to each other through those. So if you have this 2 cluster, you're running in 2 clusters with 2 pods each, you'll end up with these 4 load balancers, and each pod just has to talk through the correct load balancer when they want to talk to a certain pod. And you'll notice this does potentially add some extra hops to the data path, but most load balancers are reasonably efficient. And so this works even when we don't have pod-to-pod communication, and it solves the problem from the past solution, that it continues working even as pods move around the cluster. It lets you survive machine failures and machine replacements more easily, because the pods can be rescheduled, but they're still reachable through the same load balancer. And this means you don't have to configure anything else other than those load balancers themselves, because the load balancer's addresses never change. So it's giving you that stable, persistent network address that we need. It has a number of cons, though. So you do have to provision a lot of load balancers if you're running a lot of processes. This can get expensive. It can be a pain to do, and it can get expensive if you're running a lot of them, or if you're passing a lot of data through them in the cloud, because the cloud load balancers aren't free. And you do have to do a bunch of manual setup work up front in order to get all these load balancers set up, and to tell each pod what its load balanced IP address is, because each pod needs to know its address so that it can tell other nodes where to reach it. So you have to use a pretty fancy config map in order to pass this into the pods dynamically, which you probably won't be able to do without looking at the docs. This also means that whenever you want to add new pods, you want to scale up, you have to first create that load balancer for the new pods. And if you forget that, then your new pod isn't going to be doing very much. It's not going to be reachable. And again, this can add some extra hops on the data path unless you have a very sophisticated load balancer. But this is a very, very good way. The customers that have been using it haven't run into any production issues caused by this setup. The networking has remained reliable. Pods have been deleted and recreated on different nodes, and things have continued working just fine. So this is somewhat battle tested. You could, if you have pod-to-pod connectivity between clusters, just use the pod IPs directly. You aren't given a persistent name, so this only works if your piece of software can handle having addresses change underneath them. So you have a pod running at one IP address, it gets stopped, gets started up with the same storage but a new IP address. It needs to be able to inform all the other nodes about its new IP address, and they have to be OK with that. But if your software can do that, then this works. You need to create one load balancer up front such that they can find each other in the first place. So you have one join address that you provide to Cockroach that it tries to connect to when it starts up if it doesn't know any other members of the cluster. But once they connect to each other, they can talk directly to each other using those IP addresses if your network offers this to you. I don't know of anybody using this in practice, but it is a pretty effective way of doing things. The big con, though, is that because those IP addresses are changing, it's hard to create TLS certs that are valid for the nodes. Because whenever you sign a TLS certificate, you have to sign what addresses it's valid for. And those addresses are going to be changing every time the pod moves to a new IP address. So you'd have to sign a new certificate for that new IP address every time a pod moves. And you'd have to set up some sort of automatic certificate signer to do this. And it's pretty questionable from a security perspective, because you probably don't want to be blindly signing certificates that have root on your database cluster all the time. So we don't know of anyone that's actually doing this in a secure way. But I've run a number of insecure clusters like this that don't use TLS, and it works pretty well. But say we want to run secure nodes in the same way, where the pods talk directly to each other, taking advantage of that pod-to-pod connectivity when it's there. How do we add those persistent names? And typically, when you want to add a persistent name to something whose IP is changing, you use DNS. That's the natural solution that's been around for a very long time. And the way that DNS works in a single Kubernetes cluster is that a pod tries to talk to some service. In this case, pod 0 is trying to talk to the pod 1 service. KubeDNS knows about all the services and endpoints in the cluster because it's been watching the Kubernetes API server. It will then return the IP address of that service if there is one. And for stateful sets, it actually can return the IP addresses of the pods themselves using what's called a headless service. So we could use CoreDNS to watch multiple Kubernetes API servers at once. So CoreDNS has a plugin infrastructure, which allows you to modify the way that it works. And I should say that CoreDNS is a different implementation of the DNS for Kubernetes clusters. By default, up until 1.13, Kubernetes clusters use what's called KubeDNS, which isn't quite as extensible. But CoreDNS lets you put in arbitrary plugins into how it works. And there's already an existing plugin called Kubernetes that was written to do exactly what we want. You can configure it to the CoreDNS instance to connect to multiple Kubernetes API servers from different clusters. It can then serve DNS lookups from all of those different clusters. However, it turns out that actually doing this in a managed Kubernetes offering is next to impossible. I couldn't figure out how to do it, how to replace KubeDNS with CoreDNS, because the built-in add-on controller ensures KubeDNS is always running and does not like you trying to change it. And you could try to reconfigure the DNS settings on every node in the cluster, to talk to a different DNS server. But then you have to be constantly updating that in users' clusters every time the nodes restart or are recreated, which might work if you control all the nodes. It's tough for me to help other people with if they're running in the cloud. You also would probably want to give each cluster a unique cluster domain in DNS. So if you've ever looked at the full DNS name of a service in Kubernetes, you'll see that it ends in .svc, .cluster, .local. You can actually customize that, but you have to be able to change the flags being passed to Kubernetes components on all the nodes in order to do so, which is, again, very hard to do in a managed service offering because they control all that. They're going to recreate the nodes underneath you. It's tough to do yourself. This might become easier now that CoreDNS is the standard, but it still doesn't give you a way to modify the cluster domain. And also, the default version of CoreDNS that's shipping in these new clusters doesn't include that Kubernetes plugin that you would want to be using. So you'd still have to try to replace it. So this is a bit of a non-starter in a cloud provider. But if you're running your own cluster, this would be a great way to do it. Another variant of that is that you could try running CoreDNS alongside KubeDNS. Tell KubeDNS to defer the lookups for certain suffixes, or maybe even for all suffixes, to CoreDNS. And then you'd have to configure CoreDNS to watch all the other Kubernetes API servers. And then it could serve the responses from multiple clusters. I haven't actually tried this, so I'm a little fuzzy on the details. But I think it would work out pretty well. If someone tries it, let me know afterwards. The only downside of this is that you do have to copy the API server credentials for all of your clusters into all of your other clusters. Because CoreDNS isn't able to get the resources from the other clusters unless it has credentials to do so. So you're putting all your cluster credentials into each one, which means that if someone breaks into one of your clusters, they could potentially get the credentials to access all of your other ones. If you're smart and only give read-only credentials, this is probably fine. But you have to be careful and make sure you don't give root on all the other clusters or something like that. Or you can use a built-in KubeDNS feature called stub domains. So KubeDNS offers this feature that allows you to defer lookups for certain DNS suffixes to other name servers. And so you can, example, configure KubeDNS in your local cluster to say, I want all lookups that end in, I think I got the SVC on the wrong part of that there, so sorry. But that end in US East 1.svc.cluster.local to go to the US East 1 cluster's DNS service. And I've put together some scripts for people to try this out on GKE. And so the stub domain configuration is very small. You just give it a suffix, and then you give it an IP address that you want all DNS lookups for that suffix to be redirected to. And so again, this is how a single cluster DNS lookup works. In this solution, if the DNS lookup is for something with one of those other suffixes, the local KubeDNS will act as a recursive resolver and forward that DNS request along to the other KubeDNS server, which will then hopefully have the response for you and propagate it back to you. So in this case, pod 0 in the first cluster would get the IP address for pod 1 in the second cluster, and then be able to talk directly to it, assuming you still have pod-to-pod connectivity. So this is really great, except for one big con. So it has no overhead on the data path, except for the normal overhead of using Docker versus host networking. It's very resilient to hosts being added and removed, or pods being moved around. You don't need to add any extra software to your cluster, and it's actually completely scriptable. You have to pass in you have to configure kubectl to be able to talk to your clusters, and then you can run this script, and it will just work for you. A minute or two after running the script, you'll have a working multi-region Cockroach cluster. The big problem, though, is that you might have noticed I kind of papered over how the DNS server in one cluster finds the DNS server in the other cluster, because those DNS pods can move around as well. And so you need to create some sort of persistent address for those DNS pods. You can use a cloud load balancer for this, and then you're sort of deferring the problem such that only DNS lookups have to go through one of these load balancers, and you don't need as many of them. And so you can do that on GCE. That doesn't work on Amazon, though, because Amazon's load balancers give you, at least their standard ELBs, give you and ILBs. Their standard load balancers give you like a DNS address rather than an IP address, and you can't give kubedns a DNS name for these stub resolvers. You have to give them an actual IP. So I haven't gotten this working on Amazon, but it does work on Google, and we do have a couple of users running like this. And I've had a long-running cluster like this for a while, and it's still been working fine. Again, many of you might have been asking up until this point, like, why aren't you using Istio? And Istio has been working this year very hard on a multi-cluster mode to handle this problem of addressing. They don't try to solve the pod-to-pod connectivity right now. They just assume that it exists, and they're trying to solve the naming issue and all the other things that they solve beyond naming. I mean, they do much more than just that. And the way that it works is that you install Istio in one primary Kubernetes cluster, all of the Istio control plane components, of which there are many, and then you install the special Istio remote component in your other Kubernetes clusters. You might notice already that this means that if that primary cluster goes down, the remote clusters no longer have a leader. Maybe this has changed, but last time I looked, this was still the case. And this does look like it's going to be the best way to do things as it continues to develop. It'll be a well-supported way of doing this. There's not going to be much overhead on the data path, and it will be very resilient to changes. As of last time I've tried this, though, you were still running the entire control plane in a single cluster. The setup process was very involved. And even after you went through their long docs page on how to set it up, they still say this might need more work if you're using it in a production environment, because there are some concerns around actually solving this naming problem for the Istio components themselves. So just like we had to put in a load balancer for DNS in the past solution, you might have to do that for Istio in this solution. And again, just like using core DNS, you have to copy the Kubernetes credentials into that primary control plane cluster. So all your Kubernetes clusters are going to have their credentials in one cluster again. This isn't a great idea for Cockroach in particular, but if you're running your own stuff, you can always do your own thing. So set up your own custom DNS servers outside of Kubernetes. Maybe you could use like console for service discovery to do this outside of Kubernetes. Or set up your own auto certificate approver so that you can create a new certificate every time a pod changes its IP address. Do all sorts of different things on your own. Run your own proxy to provide this pod-to-pod connectivity. But it's tough for us to widely recommend any of these in particular, so I haven't really explored this space that much. And so to summarize, multi-cluster networking is still very complicated. There's not like a clear solution. And because it's been left so unspecified, it's really tough to know what you're going to get out of any given Kubernetes installation. It's not going to be the same from one installation to another. And not much has been done about it until this year when a few services have started paying attention to it, which I'm really excited about. So Istio has been working on it. The Cilium networking project that I talked about has their cluster mesh mode that they implemented. There's the Upbound Startups cross-plane project, which was announced recently. They're working on multi-cluster and multi-cloud use cases. And so I'm really excited to see this start to get more attention. But it is hard to recommend a single answer for everyone. So you really need to understand Kubernetes well and understand the different options if you want to implement this yourself as of today. So thank you so much for coming. If you do want to see more information on this or try it for yourself, we have documentation about it on our website. We have all the scripts and config files in our repo if you want to see it. Or you're always welcome to reach out to me if you've tried this or you've had any questions. And I will be hanging around after the talk if you have anything you want to talk about today. Do we have any time for questions? Thank you.